Okay, yeah. So welcome to the last talk of the series. The last talk will be given by Thomas Seiller. He'll be talking about invariants for group actions, logic, and complexity.
Thank you. So I will start with a few warnings. So the first warning is that this talk is not really about GCT, or at least for the moment. Maybe, hopefully, at some point we'll realize it is a bit about GCT. The second warning is that I will not be using the material. Well, I'll not be using the mathematics we've been learning through the lectures. So not about algebraic geometry. And in fact, it uses a lot of material that maybe you don't know. So the challenge for me is to try to give you a rough idea of the whole story, and maybe point out to a few notions that might be related to the GCT approach, and to motivate why I'm interested in this, right? So I'm from a galaxy far, far away from GCT. So initially, I'm working in logic. So that's why there's the logic word in the title. But I will try to not talk a lot about logic, right? I will just give a few elements as to why we come to this setting. So I will start with a few things about logic, but hopefully very easy. And then I'll just forget about it, right? So the first part of the talk will be about some background, and this is where I'm from initially. Sorry, I already start to do something. So it's about the Curry Award correspondence. So I don't know if you've learned about this. It's also called the proofs as programs correspondence. And I'm not hoping that you will get all of it in the 5 minutes I will spend on it, but I'll try to give you a rough idea of how this works, and then we'll build on that, right? So this correspondence is a correspondence between logic and computer and computer programs. I won't specify exactly in which setting, but and the point is that there's several layers to this, and the basic layer is that you have logic on one side, let's say computer science on the other. And then you have, in logic, you have formulas. And in computer science, you will see that as types. So one very simple idea, one very simple example is that if you take the formula for all x, x implies x implies x implies x. So this formula, I will tell you, corresponds to integers in unary representation. So I choose the unary representation because it's easier to explain. Of course, we have others. And once you have formulas corresponding to types, you will see that proofs, so in a formal system that I won't explain, of the formulas corresponds to programs of that type, right? So it's a functional approach. So basically, an integer will be a program itself. So what you will have is that a proof of this formula, so I will call it NAT because it's for natural numbers. And if you look at the proof, a formal proof, so if you've seen a bit about formal proofs, you know that it's like trees, right? So you use several rules that to derive some conclusion. And so I will look at cut-free formulas, so proofs that do not use a specific rule. And these proofs actually correspond to programs, and these programs are very easy to see in this case. So these are programs that take a function f, and give you f to the k for a given k. And this will be how you represent integers, right? So you can see that in the formula, because let's try this one. So in the formula corresponding to natural numbers, you see that you have x implies x. So you give a function, and then you have to produce a function as output, right? So what you say is that you take f, yellow is not good, green. So you have an f here, and then you produce a new function. And the way you can do this with just f is by iterating f a number of times. So you have an exact correspondence between natural numbers and the proofs of this formula. And what I'm interested in is the third part of this correspondence, which is not always explained. It's that the dynamics, so you have a normalization procedure, and this corresponds to program execution. Okay, so how does that work? So now you have, a proof of net of the formula net, and we've seen that it corresponds to some integer n. Then I can take a proof of this, which is basically the formula net implies net. So it's a formula for a program that takes natural numbers and produce a new natural number. So you see that as a program, and then you have this rule, which is called the cut rule. And this gives you a new proof of this formula. Okay, so this is because this and this disappear. And what you have is normalization procedure. So you have some kind of rewriting that gives you a new proof of the same conclusion, but without the cuts. So this gives you a new natural number, right? So the fact that you eliminate this cut corresponds to computing the value of the function, right? And so this corresponds in the program side to taking p, giving it n as input, and then reducing, so executing the program, computing actually, and providing the result. And you have an exact correspondence. So this means that the length here is equal to the length here. So what you have is the procedure you have on proofs actually corresponds step by step to computation, right? So that's the proof as programs correspondence. So I didn't say it, but please interrupt me if anything is unclear. So why I'm interested in this initially, so this led to some results in logic where you take a logical system and you restrain it in some way, which imposes some constraints on the proof normalization procedure, right? So given a logical system, so for instance, you can, let me give you a concrete example. So you can take a logic, which is called SLL. I won't explain why, but you can ask me later. And this logic imposes that the length here is bounded by a polynomial. So the logical system imposes the complexity bounds, right? And so this is part of a field called implicit computational complexity. Okay. So this is the background, right? And now I will just forget about logic, and I will explain why. Because so when I started doing my PhD thesis, I worked on mathematical models of proofs and the dynamics of proofs, right? So it's this procedure of elimination. And I worked in a with quite complex mathematics, which is von Neumann algebras. So I don't know if you know about von Neumann algebras. Let's say if you don't know about it, just think about a matrix algebra and you'll get most of the ideas right. Okay, so it's a kind of matrix algebra, but for infinite dimensional spaces. So usually, let's say, just to give a formal definition, so it's a subalgebra of B of H. So this is a Hilbert space. This is bounded linear operators. And this is a subalgebra closed for some topology. Let's say weak operator topology. Right. So it's a pointwise topology that you can define. So one very simple example, if you want, is you can define a von Neumann algebra by taking larger and larger matrices. Okay. So you take the limit of this, where you embed A as AX0, 0. Okay, and you take the projected limit with a closure for the topology, and this gives you a very standard and well-known von Neumann algebra. So why von Neumann algebra, right? So if you take a von Neumann algebra like this, it's standard, it's very round, and you take just the unit ball of the von Neumann algebra. Then there's a way of representing proofs in this, right? So in the sense I just explained before. And to represent the proof, you need to fix both a von Neumann algebra and a subalgebra here, right? A maximal abelian subalgebra. So if you fix A included in AN, then you can embed proofs. Okay, but what we cared about is how you compute. So the proof normalization. So the proof normalization translates as a functional equation. Okay, and you know how to solve this equation in the subset, in the purple subset, right? And then there was a result. I think it's 2000. I checked before, but I can't remember. 6 maybe, by Girard, which says that this functional equation always has a solution in the set, in the whole unique ball, right? So the result, the solution to the equation extends to N1. So that's the point where we just forget about logic. It's still there, but basically the idea is that if you take a logical system and you see which programs correspond to it, you have a restriction. So basically these are the programs that you can prove correct, right? You have a finite proof that they actually compute what they are meant to compute. And so this is too much of a restriction. So that's why it's not really interesting in terms of lower bounds usually. But here what you do is say, now I can use the unique ball of a von Neumann algebra and think of every operator there as a kind of generalized program, a generalized proof. So you include programs that do not correspond to proofs, right? And you have a notion of program execution on that. So the point is that now you can see this inclusion plus the equation as a model of computation, right? So you have elements. These are the operators, and you have a way of describing how they compute. This is the solution to the equation. And then there were a number of results that explain that if you change these inclusions, so changing the inclusions imply a change in the expressivity of the logic corresponding to it. So a change in the complexity class it captures. Okay, so we have examples in which we have a Turing complete model, so you can compute anything. We have an example where you take an inclusion like this and you get only elementary functions. We have examples in which you have log space, and we have several results like this, right? So this leads to a question, which is there a way of understanding in which cases you get the same complexity classes, right? So you take A1 included in N. Sorry, my N's are really bad. A2 included in N2. And you ask if they characterize the same complexity class. Are they equivalent in some way, right? That does not talk about complexity itself. So is there a notion of equivalence for these objects or these inclusions of algebra that would not capture, but at least be implied by the fact that you get the same complexity class? That's the first question, right? But so the point is that this question is very, very complicated. And the reason is that if you take von Neumann algebras, these are already very complicated. And you try to understand these inclusions of subalgebra, of maximal abelian subalgebras, and this is even more complicated. So you get lots and lots of open questions, and you just realize that why am I going through this? I'm not sure that will give me answers to my questions, right? So it will just lead to more complicated questions. So this is where we go to group actions. So one way of trying to simplify this question is to go through a known construction of von Neumann algebras. So von Neumann algebras actually arise. So there's something called the group measure space construction. And it's a very old, so it's Murray and von Neumann. In the 40s, there's a series of papers in the 40s where they start studying von Neumann algebra. So it was called, the papers are called rings of operators. And they have this way of producing a von Neumann algebra from a group action. So it's a group action and a measure space, right? And I will try to explain a bit how it gives you the inclusion and how it's better for us, right? So the group measure space construction is you have a group, it acts on X and measure space. Let's say this. And usually you will ask that the group acts by measure preserving maps. And at some point we'll forget about these restrictions, but for the moment, to get von Neumann algebras, you have to go through this, right? So how do you get something with this? So there's the first remark, it's that if you take L infinity of X, so this is the set of functions from X to C, such that the supremum norm of F is bounded. Right? So basically, there's a value for which almost all for which f of X is bounded by this value for almost all x, right? And this can be seen as a Van Neumann algebra. So it's an abelian Van Neumann algebra because you can see it as a subspace of B of L2 of X. So basically, this is, you take the function and you just multiply with this element of infinity, and since the norm is bounded, then the operator you get is bounded also, right? And the action of G lifts to an action on L infinity, right? So you can actually, you have an action of G on L infinity. And so you can do something that's called the Crust product construction, which I will write like this, right? And this is a Van Neumann algebra. And I won't explain, but if you have several specific properties on the action, then you know the algebra will have some properties as well, right? So in some cases, it will be a finite Van Neumann algebra. In some cases, you will have a factor, but I can't go into these details, right? And L infinity of x mu still sits within this, right? So the group action actually gives you exactly what we had before, right? So it gives you n with a maximal abelian Van Neumann subalgebra here. So the group action actually gives you what you were considering as a model of computation before, right? So I will now just give intuitions as to why this is actually a model of computation and how you can see this very easily. So I will forget about some constraints. I will just look at monoid actions. M on X as a model of computation. So the idea is very simple. I will just give an example. It's that X is the set of possible configurations of a machine, and then G, oh, now it's M. M is generated by basic instructions. So the basic example of model of computation is a Turing machine. So let's do that. So you take X as a set of Z-indexed sequences of 0, 1, and star, right? So star is for the empty, is this the blank symbol, right? And you take this subspace with where almost all symbols are star. So you just have finite numbers, zeros and ones. So these are basically what the configurations of a Turing machine tape should be, right? And now you can define functions from X to X that will correspond to basic instructions in the Turing machine model, right? So for instance, this is a shift. So you take the sequence AI and you produce BI with BI equals, so we go to the right, so it should be AI plus 1, right? So the idea is that the symbol in the 0 index is where the head of the Turing machine is. So this is where you read. And then you just shift the sequence, and this is the same as moving the head, right? So you can do left, of course, this is basically the same. And you can define, for instance, right 0, which is also a function from X to X, where you take a configuration, AI, and you produce BI with B0 equals, so this is a 0, 0, and BI equals AI otherwise. You see, this is very easy. This is how you would think of this monoid action as the model of Turing machines, right? So if this is giving you the model of computation, you have to explain what a program is, right? So again, this is a complicated notion, so I won't define it completely, but I will give you a specific case. So a program then is what I call a graphing. So this is a notion coming from ergodic theory initially. And it generalizes dynamical systems. Okay, so I will just restrict to the dynamical system case, which is basically when you're just concerned with deterministic programs, right? So the point is that if you restrict to the deterministic case, what you ask is that the program is a function from x to x. So you have for reasons that you will understand, you have to add a space, which is control states, right? And then this is just a function from x times d to x times d. This is the transition function of the Turing machine, right? And you see that as a dynamical system. So it's actually a dynamical system such that the graph of f, right? So the set of x, f of x, is contained in the set of x. Yes, I will write this like this: m of x for all m in n. Oh, sorry. Okay, so you can the programs are dynamical systems which are constrained in some way by the group action, by the monoid action, right? So this is a way actually of writing concretely the elements of the van der Waals algebra we were working with. Okay, so it's a more concrete way of seeing it, and you can actually take a Turing machine, a concrete Turing machine, and write the transition function, and you can build this dynamical system. Okay. So at this point, we have a model of computation, we have programs, and well, we want to do the same thing we did before, right? So these group actions or monoid action should correspond to some logical system, right? And this logical system actually explains, it describes the set of programs we just defined. And this logical system gives you a complexity class, right? So the principle is you take alpha, which is a monoid action. This gives you a logical system. I won't explain how. This is very interesting, but I don't have time to explain how you get this. And so you get actually a complexity class, because you look at these dynamical systems, okay, like the ones that satisfy the constraint that I explained, that can be given, sorry, the type net to booleans, for instance, right? So these are the dynamical systems in which compute a predicate on natural numbers, a decision problem. Okay, so I write this as CC of alpha. So this is basically the same thing as the van der Waals algebra, but it's more concrete. Now we can actually take a concrete model of computation and try that, right? Which was difficult with the van der Waals algebra case. And so the question now translates as if CC of alpha is equal to CC of some other action beta, does that imply that alpha is equivalent to beta for some equivalence? And the equivalence I'm interested in is called orbit equivalence, right? Yeah, this is orbit equivalence. And orbit equivalence is basically saying that you have a measure space isomorphism that maps orbits to orbits. Okay, so here we arrive to the question that basically drove me for a few years, which is, can we actually prove something in this direction, right? The reason why it's interesting and why it's backed up in some way by results is that I can actually produce a number of actions. This of I, of infinite omega, beta, and gamma, right? And if I look at the deterministic case, right? So I restrict to the dynamical systems. Then the complexity class is corresponding. So CC of alpha is a sequence of languages that are defined by, so here it's automata. You get log space, you have p time, and here you have p time again. Right, so I can prove that for some concrete actions, I get this. And these actions are actually extensions. So this is an increasing sequence, right? And so the known results in this, so that there are results, and we know that this part of the hierarchy is strict, right? This is some automata classes, and there are proofs that they are distinct. And we can actually prove that this, so there are invariants that prove that these are non-orbit equivalent, right? I will just give you the extension. So if you look at the non-deterministic classes corresponding, then you get, the regular languages again. Now you have some non-deterministic versions of these. You have NL, you have P time again, and you have NP. Okay, so and there's also a probabilistic version of this. So the idea is that if we can show that even in some cases this question above is true, then, well, this statement is true, then this might explain some separation results, right? So of course this is where I was like a few years back. And the first question you have to ask, so people ask you about barriers. So I won't talk about them, but this is a good question you can ask me later. So this is where I was, right? And I would like to prove in some way that this is true. And so I started to look at other things, and basically I started to look at GCT. Because there are orbit actions, questions of orbits, group actions, and everything. So I was wondering if there was some connection there. I still can't tell you, but maybe you can tell me. And hopefully there will be. So for instance, for the moment, I just looked at actions on measure space or topological spaces, but actions on some more complicated spaces like varieties or vector spaces is possible, and the whole thing works, right? So the setting is very general, so maybe we can actually look at this. So, but I looked at GCT, and to be very honest, I'm from very far away, so I didn't understand anything. So I went back to the first result. So the result that is said to be GCT 0 in some way, which is lower bounds on PRAM without bit operations. So, so I will talk about this now. So lower bounds and entropy. So I tried to go through this paper of Melnay, right? So the lower bounds for PRAMs without bit operations. And at some point during this, so, as mathematicians, we usually try to take something and write it into the language we understand best, right? So I looked at this result and the proof, and I tried to fit it into the way I think. And at the time I was thinking in terms of dynamical systems, right? So I arrived to this idea that you could rewrite the proof, and that some invariants for the dynamical systems actually were used in the bounds you get, right? And this invariant is called topological entropy. So I don't know if you know topological entropy, so I will give a very brief idea of what it is. So a dynamical system is a function from x to x, right? What you care about are the orbits. And when you think in terms of what we've been doing, the orbit is actually the trace of a computation, right? So you take a point in the space, a configuration, and then you look at how it evolves through the transition function. So we care about the orbits, and topological entropy is about orbits. And it's about something quantitative about orbits. It's about how many orbits are created when you apply F, right? So let me explain this. You take X as a set, so it's a topological space, and you take a cover of it, an open cover, right? So let's say with 2 sets only. And then F is continuous, so you can look at the inverse image of this, right? So you have U, you have V, and now you have F minus 1 of U, F minus 1 of V. Now you can, so my drawing is not good. Let me redo that. U and V. And now you can look at the intersection, so the pairwise intersection of these 2 covers, right? So in some cases, this will have 4. So this example, you start with 2 subsets, and now we have 4. And you continue, you will get 8 and 16, and okay. But in some cases, you get actually less than that. So if you take UV and now you take the identity, what you get is UV back. So you just keep going with just 2 subsets, right? So the idea is that what you're doing is you're taking your space and you have some kind of blurring glasses, right? So you cannot see the whole space. You can just see finite information about it. So you just know that there are points in U and points in V, and then you try to describe the behavior of the function in terms of these U and Vs, right? So if you look at points in this, then you have 4 types of points. You have points that are in U and will be mapped to points in U, points that are in U and will be mapped to V, etc. Right? And in some cases, points that are in U are not mapped to V. So what you do is you take the smallest, so you look at the cardinality of the smallest cover, and you keep that number. Okay, and you do that for every step. So you can continue like this. And here you will take the cardinality of the smallest corner. So now I will have to look at the cheat sheet because I can't remember the formula each time. But if you take the logarithm of this, right, and you take 1 over n here, then you can prove that this will have a limit. Okay, so the limit of this is called HF and C, which is the starting cover. And then the entropy is the supremum over finite covers C of HF. And this is actually a way of explaining how the number of orbits grows. So it's the exponential rate of the growth of orbits, right? It quantifies this. So for instance, if you take the identity function, you get 2 each time. So in the end, you get the entropy is 0, right? Because the number of orbits never grows. But if you take a very complex function, then the entropy will, you can have entropy equals to infinity, Okay, and you have functions in between. So you will say, what's the point and what's the connection with lower bounds, right? So the connection is here. So now you take M, a machine, and you can get, so using the machinery I explained, you can see this as a dynamical system. Right, and this dynamical system, it mimics, so it shows every step of the computation of n, right? So if you take the dynamical system once, you take one step, you apply it once, then it's the same as doing one instruction in the machine, basically. And now you look at this. So you take the same kind of things, and now you separate the space, and you would just look at the points that will lead to acceptance and the ones that reject. So if you've ever seen the proof, the lower bounds proof for algebraic computational trees of Steele and Yao, or the Benner version, then it's basically what we do here. So we actually capture these also, right? So you look at, you separate the subset into accept and reject, right? And now you go back. So you will get the points that are sent to accept in one step, the one that are sent to reject in one step, and you do this thing where you just do the intersection of the covers, right? And you continue like this. And after a number of steps, you get a decomposition, right? Mm-hmm. Of the space. And this decomposition in a number of cells, right? And the point is that the number of cells is bounded by an expression in the entropy, right? It's bounded by a number that depends on the entropy of n. Okay? And now, so what you have usually is you have, for instance, in the Steele and Yao lower bounds, you have these cells are actually semi-algebraic sets because the boundaries are given by polynomial equations or inequations. And so you know that you have a bound on the degree of the polynomial equation. And this gives you a bound on, on the number of, so I will write that's beta 0, right? Of a cell. So if you have a cell, you have a bound on the number of connected components of that cell, right? Mm-hmm. And so these two bounds together give you a bound on the total number of connected components of this decomposition on the left. I will take another color, right? Mm-hmm. And now the proof is, if you want to show lower bounds for a problem, then you have to realize that this decomposition has a meaning in terms of computation. So what does it mean for 2 points to be in the same cell? It means that in the case steps that lead to accept or reject, they will not be distinguished by the machine, right? So the machine will apply exactly the same sequence of instructions. So 1 point is accepted if only if the other is, right? So that means that if your machine computes a subset in case steps, this subset is actually described as a union of these cells, right? Mm-hmm. So now you take a problem, a subset with a large number of connected components, and such that the complement has a large number of connected components, and then you get this. You get that to produce enough connected components, you will need to go through at least that number of steps, right? Is that clear?
Yeah.
So this is the basic idea of the proof. And you see that there's this notion of entropy that connects, right? And the notion of entropy actually, I think, goes further, but I didn't write it yet. That in fact, the degree of the polynomial equations can be seen as a sort of algebraic entropy, right? So the idea would be that there's this notion of entropy that captures what is necessary to get the lower bounds. So you take this idea and you formalize it, and you can see that, so there's this Steele and Yao results from 82. The proof of Cooker that NC on the reals is separated from P on the reals actually uses the same technique, so you can rewrite it that way. And then you have normally 99, right? And then what we did is we realized that, so Steele and Yao was actually refined. So it's a very simple idea, right? It was refined by Benor to include divisions. And you can do the same thing. So in this formal setting of topological entropy. And so you can, in the Cooker case, you don't get anything else. But in the Mermeli case, then you can extend the results with division. And actually, you can take arbitrary rules also, right? One point is that, so there's a paper about this, but you should look at the version on my website because the archive version is not updated. So you extend the results, but on the real numbers. And at some point I thought that it lifts to the integer case, but it doesn't. And actually you can show that the Euclidean division is not computable in this real version. So you have a strict inclusion in some way. So, but that needs to be written down. So we have the proof, but I didn't find the time to write it down yet. Okay, so just to conclude, I will try to explain how it fits into this whole idea that I explained until now. So you have this thing that CC of A is equal to CC of beta. And you ask whether this implies orbit equivalence, right? And in fact, there's another notion of equivalence on group actions, which is called conjugacy. And conjugacy has an invariant, a known invariance, which is topological entropy. So it's an invariant for this, right? So it's a way of proving that two things are not equivalent for conjugation. And we know that this implies orbit equivalence. So maybe by understanding better the lower bounds here, we could have some kind of even stronger thing, which would be the implication here, right? So maybe I'll stop because I think, unless, no, oh, sorry, I didn't see. So I have 10 minutes, so it's good. If you have questions. Yes, but maybe I will take questions if that's okay. I can explain lots of things, but I think it's exerting material, so it's good to stop here. Okay.
Yeah. Thanks. Thanks, Thomas. Yeah. Are there any questions for Thomas? Yeah, so I have some silly question. I mean, I don't. Maybe it's a silly question. I don't. I got some part of it. Yeah, but so you were looking at monoid actions. What if I make a bigger structure? So I look at group actions on your set, monoidal actions. Then what happens actually?
Yeah. So I said that everything works with monoid action, but if we look at what's here, so the results, for instance, all these Group actions. So there's only one which is not, right? So the point that in the von Neumann algebra setting, to create a von Neumann algebra, you need a group action. And so sometimes you can, so maybe there are constructions in which you can weaken a bit the structure, but not to a simple monoid, right? And it's, so what I didn't explain actually is that this orbit equivalence, it's an invariant for the subalgebra, so the inclusion of von Neumann algebras that I talked about earlier, right? So it's really related to this question, and the orbit equivalence question. So we have mathematicians have developed invariants for these, right? And so we know how to separate some actions for this. So for the orbit equivalence, we have so for groups, and here you need groups. We can define, so there are invariants known. And for instance, there's the L2 Betti numbers. So this is defined by Gabriel. So you can compute some kind of Betti numbers. So I'm not sure you've seen L2 Betti numbers, but so basically Betti numbers are the dimension of the homology groups, right? Yeah. And in some cases, these are infinite. So in the infinite case, you cannot separate manifolds in this way. And so I think in 72, Atiyah actually came up with this idea that instead of looking at the group, the homology group, you generate a von Neumann algebra from it. And in von Neumann algebras, you have a notion of relative dimension. So even when the dimension of the group is infinite, you might get a finite number corresponding to it. And so these are the L2 Betti numbers, and you can separate manifolds in this way when the usual Betti numbers don't work, right? So in this case, it's again it's cohomological invariance. So there's I think maybe that's something I didn't quite explain also, but in some way there's cohomological invariance coming in, right? And I would like to formalize this in some way. And there's also this connection that the orbit equivalence is really related. So the notion of orbit is actually really related to the construction of the logical system. So I couldn't go through these details because it's too involved, right? But when you construct the logical system, you actually use a two-cocycle relation that relates the execution of programs with the zeta function of the dynamical system. And the zeta function actually, is defined in terms of the finite orbits of the system. So there are all these ingredients, and I'm trying to get them together and understand if we can actually say something here.
So does this make sense for, von Neumann algebras that we understand well, like group algebras and maximal sub? If I look at, I'm coming from a very different world, but if you look at the way people understand, one way of understanding, say, representations of the symmetric group are to look at the group algebra of the symmetric group, and inside it look at a maximal abelian subalgebra, actually. Okay. And those maximal abelian subalgebras actually give rise to fairly nice idempotents, actually. And that they finally, so one way to understand this entire representation theory of SN is through this, what are the certain kinds of bases, actually. So what Kunkov and Vershik called the Juicy-Murphy basis. And so, do these things, do concrete examples make sense? Can I?
Yes, so the point is that in the examples we have, the von Neumann algebra generated is not finite.
Is not finite.
So, in fact, it's finite in the sense of von Neumann algebras, but it's acting on infinite spaces, infinite dimensional spaces. So maybe I can say a few things. So when you look at matrix algebra, you can ask what's the maximal abelian subalgebra here, right? And this is basically the algebra of diagonal operators in a given basis. So these inclusions actually correspond to bases, right? And you have the same kind of idea when you go to the infinite dimensional setting. So you take now a Van Neumann algebra and you think of A as a sort of basis. Now, when you define the operators, when you define the interpretation of the logic or the programs, what you care about are actually, it's called the, so let's do the first. So you can define it in two ways. So you take the normalizer of A. The normalizer of A is the set of operators that send projections in A to projections in A, basically, right? And this generates a Van Neumann algebra. So in the matrix case, if you take the Van Neumann algebra generated by this is MN of C. So it's a very nice case and everything works well. But in this case, actually, if you take the normalizer, so there are good cases in which you get N. And these are called Cartan subalgebra. But in other cases, you just get R, which is a subfactor of N. And the worst case is when you get A itself. But this is very counterintuitive when you think in terms of matrices. So the way I think about it is that it's a basis that's so twisted that you cannot actually find unitaries that maps projections to projections, right? So yes. So the way I think about it is that the algebra, the A is like this, and the normalizer is, these are the operators that can send elements there. And if the algebra is too twisted, then there's no unitary that works. So you would have to go to a limit and then you have nothing. I think it's a good intuition there. But so basically you have this idea of basis and it comes in, right? And in this case, it corresponds to the space of configurations. So the basis corresponds to the configuration, to the measure space.
Got it.
It's related. So when we look at the inclusions there, for instance, so I have a paper that explains that depending on the case you are here, so this is called the singular case, you get different logical systems. So you get different expressivity depending on how the subalgebra sits into the big one, right? So I'm not sure it answers the question, but I think they are the same kind of objects coming in, right? But the situation is much more complicated because of the fact that you have this finite, this infinite dimension.
Infinite.
Yes. But so yes. So let me say one thing, which is the finite Van Neumann algebras are actually the ones in which the projections are finite in some way. So if you take a projection, you can say it's equivalent to another one, if and only if there exists a unitary, mapping one to the other. What would it be? U pi equals pi prime u, something like this, right? So you can map one. Oh, let's do it like this, right? U star u equal pi. So you can say that two projections that are equivalent if you find an isomorphism between them, right? And so this notion of equivalence depends on the algebra. And basically when you take a Van Neumann algebra sitting into B of H, you may have pi and pi prime projecting on infinite dimensional space, right? And this is witnessed by the fact that there's U from pi to pi prime in B of H, right? But this U doesn't live there. So the projections are no longer equivalent in N. And so finite Van Neumann algebra are such that there doesn't exist pi prime strictly smaller than pi with pi prime equivalent to pi prime to pi. So there's a total order on the projections. And so you can define the notion of trace, right? The trace of matrices extends to these algebras. In the example I gave with the projective limit, the trace is actually, if you take the normalized trace, then you can define it very easily, right? So you had A, which was mapped to AA. So if you take the normalized trace, right? So the trace divided by the dimension, then this preserves the trace. So this the trace is defined on the limit. And from the trace, you can define something called the Fugler-Decazison determinant. And this is based on the idea that, so if you take the determinant of the exponential array, then this is the exponential of the trace array. Right, so you can see this easily on diagonal matrices. And using this, you can define the determinant from the trace. You have to go through some things but basically you have functional calculus, so you can define log of matrices and stuff like this. So yes. So there's also a determinant coming in, but yeah.
Are there any more questions for Thomas?
Sorry, I think I took too much.
No. Guess let's thank Thomas. Thank you.
Thank you.
Okay. Yeah. Okay, Thomas.